Okay, for the Physics 113 lab, we're going to be doing Archimedes principle this week. If I were to take any object, okay, and suspend it on a triple beam balance. Now remember, these triple beam balances work. Right now it's balanced so that if all my masses here are on zero, then I have it balanced out so that this weight hanging on this end and the other stuff that's hanging past this pivot point create torque, which we talked about torque recently, and it's balanced by the other masses that are here. So if I increase the masses over in this direction, like so, I would be increasing the torque, causing it to rotate in this direction here. So as I place masses over on this side, I would then have to move these over in this direction to balance the two out. And that's how these work. So if I were to place an object here on a string, I would get the same end result if I hang that string off the end here. It would still cause it to rotate because I still have mass hanging off on this end, okay? So if I begin to balance this out, I could find what my mass is for this object, okay? That would be close. And just the same as if I had it in the pan. But what if I were to place this in water? And so the unique thing about these triple beam balances are that they have this stand, okay? And so I will be able to place this cup with water, but it will be separate than this device. So all of this will still be able to move irrespective of the water, okay? And so I still have this set for the mass that it was before it was in water. So it's fully submerged in the water. I see that it does not pull this down. In other words, the mass is going to be less. So as I pull this over, I'll see that it's actually less mass here. So what's going on? The water has to be exerting a force in this direction to cause there to be an apparent mass that's less than what it is. Okay, so let's take a look at the diagram here. Let's say I had some mass that was suspended by a string inside this cup of water. Okay, one of the things we definitely would be able to note, we would definitely be able to see that I have a weight because the mass would be acted upon by gravity, so we would define that to be weight. Okay, then there's also going to be a tension. I'll note that up in this direction here. So we would also have a tension in this direction. And what we noticed a moment ago is if it was in air, the tension and the weight and the weight that I get would be the same. But because it's in water, we are going to note that there is another force that is acting on this object that we're going to denote as the buoyancy force, okay? So, or the buoyant force. So one thing that you would note is that as you place this object in here, you would see the water level rise because it would be displacing a certain amount of water. So you could measure this, say, in a graduated cylinder to see how much that volume of water would be. Well, it turns out that the buoyant force is going to be equal to the weight of that same displaced water, the volume of the water that's been displaced by the object. Okay, so one of the things that you may recall is that density is defined to be mass over volume. In other words, how much matter can you fit into a certain volume of space? So if we were to talk about the density of the body that we've submerged inside, so we'll put density with a little b here to represent density of the body, then I could write that as the weight of the body divided by the mass, I could define that as the weight of the body divided by g and then divided by v. So in other words, the weight divided by g would give me simply m, and so I'm just writing the density in terms of the weight, okay? So now one of the things we may want to do is look at the ratio of the weight to the buoyant force. And if I were to do the exact same thing with what I've just written here, I could write the weight of the water, or sorry, the density of the water would be equal to the buoyant force, because that's the weight of the water, divided by G to get us just the mass of the water, over the volume. So that would be another way to write that. So if we take these two and combine them together to look at a ratio of the weight to the buoyant force, we would then have W over GV, and then on the denominator I would have the buoyant force over GV, and of course G is common to these. And then the question would be, is the volume? Well, remember, we're talking about the weight of the object and the object itself displacing a certain volume of space. Well, the buoyant force is described as the weight of that same volume. So in this case, yes, the volume is the same, so that would cross out as well. So we see that this would check out to be W over B. But also recall that this is equal to the density of the body over the density of the water. Okay? So this is the main equation that we're going to be able to come up with to be able to use Archimedes' principle to solve for density. One of the things that I also want to point out here is the equation that we can get from this free body that I've drawn here. So if you look at the weight would have to be balanced out by the tension plus the buoyant force, right? So in other words, I could take the buoyant force and take the weight minus the tension. So in this case, the weight would be the mass in air, so in other words, not submerged, multiplied by G, and T would be the mass while it is submerged, multiplied by G. So I can substitute that into this equation here to give me the final one to say that W over W minus T would be equal to the density of the body over the density of the water. And if I know what the density of water is, and the density of water is 1 gram per cubic centimeter, then I could write this as density of the body would be the weight over W minus T all times density of the water. Okay? So that's how we're going to go about calculating this. I'm going to give you one quick tip. Because we're looking at the density of water being 1 gram per cubic centimeter, then one of the nice simple things we'll be able to do here is notice that W and T both would have G in them if we were calculating the forces. But I could pull out G from both the numerator and denominator of this boxed in equation here and divide through and cancel out the acceleration due to gravity. So in other words, if you will simply take the mass in air in grams, so if we let W, instead of it defining it as a force, if we define it as the mass in air and use grams, and then let T be the mass we find in water, or the liquid, and leave it in grams. This will make this a very simple calculation, because the density of water, if you notice here, is in grams per cubic centimeter, is 1. So you would simply take the mass in air divided by the mass in air minus the mass in water to find the density, because you would be multiplying by 1. That would give you the density of the body in grams per cubic centimeter. Okay, so that's the first part. We'll come back and talk a little bit more another point in just a second. So we're going to go ahead and try to take some measurements here, and I'll record that data. They would like us in step number 1, if we look at the exercises, they find the density of several sinkable objects. So this first one that I have in here, you noticed, was kind of a lighter silver color. This is aluminum. And so if we suspend aluminum in the water, and I'm going to come to the side over here and try to get the scale just right. Okay, and I see that is, we've got 10 back here, and this is 1.7. That's going to be 11.7 grams. Okay, so I'm going to make us a table, and the first thing I'm going to do is we're going to label this, the top of the table is going to be the object. Then we're going to have W, which is the one where we're finding the mass in air. I think I'm going to put these brackets here and say grams, because I'm going to write these down in grams, all right? Then we're going to have T, which is going to be the tension of the string when it's in water, when it's suspended in the liquid. So I'm going to also write grams, because that's all I'm going to record that in. Okay? And then from that point on, you'll be able to make the rest of the calculations for finding the buoyancy as well as the density. So the object, the first object is the aluminum, or in Old English, aluminium. And at this point, come over and I've measured, I saw that was 11.7 grams. So the tension when we're in water is 11.7 grams. Okay, I'm going to take it back out of the water. I'm going to dry it off real quick so we don't have any more extra mass than we need. And I'm going to just lay it in the tray. Okay, so that's 18.2. All right. Now let's move to the next object. This is going to be brass. So I'll place it inside of the loop. First thing I'm going to do is find it when it's in air. And then, in other words, I'm just going to lay it in the tray. All right, so in this case, I see it's definitely much more, more massive than the 220. Coming over till now, we're at this point, it's a little too much. Come off of that 10 and slowly move over in this direction. Pretty good. Okay, so that is 50, call it 54.0, so 54 grams for the brass cylinder. Now let's suspend it in water. Okay, so that is 47.6. All right, get rid of this guy. Next one I'm going to use is copper. So that would be 57.1. Now we'll go ahead and suspend him in water. Okay. So that's going to be 50.7. Okay, and finally, I'm going to use, it's a piece of steel, or which is almost all iron. So this is going to be our piece of iron. All right, so let's find the mass for it. All right, so that is 47.7. Now I'm going to suspend it in the water. Okay, so that's 41.6. All right, for the next part, they would like us to go ahead and determine the density of a floatable object, as they say in the lab manual. So in other words, a less dense than water object. So we have here a piece of polypropylene. If I placed it in here, it would just float. So I would not be able to displace the water completely. So one of the things that I can do instead is to place these two objects together. And my strategy here is going to be to measure W and T so that I can calculate B for the pair of them. Then because I already know B for the copper, then I'll be able to subtract it out and have simply B for the buoyancy for this piece of polypropylene plastic. Okay? So placing the two together, I'm going to remove this out of the way to make this a little easier for us now. Okay, I'm going to call that 81 grams even. Okay, so this, be careful here to lower this in the water so it'll all stay together. And going to move this cup just a little bit. Make sure that that does not rub against the sides of the cup. Okay. And notice we're going to go way down. So now we're in the 40s, and it looks like somewhere close to 49 here, a little less. All right, so it's going to be 48.4. Okay. Now, again, at this point, you can subtract these two to get B. Then also, you know the B for copper already, and just subtract that out. Then you can proceed forward with calculating the density. However, be careful because you want to use the weight of the polypropylene by itself to calculate the density once you've done that, because you remember you're going to need W again to calculate the density. So in that case, once you have B and you've subtracted out the copper from B so that you have B for strictly just for the polypropylene, then you only want to use W for this as well. So you can take the data I've got here and so just subtract off the W for copper so that you have that. So you'll subtract off both W for copper and then also calculate B for it by itself and then calculate out what the density would be. Okay, we have one final step, and that is we are going to replace the water with this liquid, okay, and this is isopropyl alcohol, 70% isopropyl, with a wintergreen scent. So one of the nice advantages for you not being on campus at the moment is you don't have to smell this. All right, so now I'm going to take the alcohol and I am going to pour that in here and hopefully fill up this container. Or at least pretty close to the top. That should be plenty. All right, then I'm going to take the copper. We only need to use one for this, okay? So I'm going to suspend the copper inside. So I'm going to start a new location here, write copper in alcohol, and T is what we're going to find. So 51.7. 51.7 grams will be the value for T. You already know the value for copper in air, not inside the liquid. So based on that, you can go back to our equations that we had earlier. This time, if I rewrite this equation to be rho of B over rho of water, in this time, instead of calling it water, I'm going to put an L for liquid, a lowercase l. And we've got W over B. And if I invert this equation, got rho of the liquid, and then multiply by rho of B, which means for the body, so rho of the body. In other words, the density of copper, okay? So in this case, we know the density of copper. In our case, we're going to use the copper here, so we know what the density of copper is from earlier, so from our experiment. And then all we had to do was measure the buoyant force, which in this case, of course, is going to be W minus T. We know what W is for copper, and now a moment ago I told you that T for copper in the alcohol was 51.7 grams. So if we multiply by the value of density we found for copper earlier, substitute in the weight of copper that we found earlier when it was not suspended in a liquid, plug those values in, we've got the density of this liquid. And then what you're going to do is compare to the known value of 0.86, okay? And we'll see how close we get for the density there, and that is in grams per cubic centimeter. Okay? So that's it for this week. Just contact your TAs if you have any questions about anything, and hopefully now you have a little bit better understanding about how density, a new way to calculate density. You've probably done it in the past where you've done the strictly mass over volume. And this is related to the idea of why something such as a battleship made of iron can float. It is simply that the amount of water that's displaced, so in other words, if the bottom part of the hull of the boat is in the water, it's that volume of the water that's displaced. If I were to draw that out here, so if I had a boat here, and let's say my water level was like so, then I would have to look at this volume here, and I would look at what that weight of the ship is compared to the weight of the water, which we called the buoyancy force. And so if it's less dense than water, it floats, and if not, okay? So that's how that would work. All right, so again, ask your TAs if you've got any questions, and good luck. Have a great week.